Alright, now that we have talked about the cubes program and we wrote the serialized version of the program, and then I just wrote the GPU code, the CUDA version of that simple cubes program or cubes kernel. Let's take a deeper look at the kernels and the way that we call them in the in our program. Remember that CUDA programming is essentially heterogeneous computing. So the idea here that we have is heterogeneous programming. And what that means is that we have two pieces of code, and then these two basically work together to program and to perform the application, the task that we have in mind. We have the host program. We call this the CPU side code, and then we have the device program, and this is our GPU side code. Now, the kernels basically happen in both areas. The kernels run on the GPU. So the kernel piece of code runs on the GPU. What host does is that it specifies the kernel functionality and also the level of parallelism on your kernel. So these pieces basically work together side by side to work and to get your program working. Now, the specifications of your kernel, this piece of process is your declaration and definition of your kernel function, right? The function that you write is the specs of your kernel, basically the functionalities of your kernel. The levels of parallelism in the processing of your kernel that your CPU controls is going to be through calling of your kernel function. So this is very important for us to understand. CPU specifies the level of parallelism on your kernel. How does that work? It works through specifying the architecture of your kernel. And that is in terms of the number of blocks and the number of threads within each block that determines how many of these kernels are going to be executed by your GPU. And then with the combination of threads per blocks and then blocks per grid, which we'll talk about a little bit later, working hand in hand with your GPU's hardware architecture, that determines the performance of your algorithm, the performance of your operation, when things are going to be associated and allocated and created and assigned to your streaming multiprocessors within each to your simpler parallel processors, or rather simpler cores in each streaming multiprocessor. One of the things that you need to remember and you need to notice is that GPU can run many blocks at a time, and that blocks of threads can have lots of threads within themselves. So the massiveness of your parallel process here is going to be determined. So this is essentially a massive number of threads that your GPU can handle is through a lot of threads within a block, a lot of blocks within a grid, which basically gives you a lot of processes, a lot of number of times that your GPU can run a specific kernel. The way that we actually encode, determine the level of parallelization on our GPU is through calling of our function, our kernel function. So the name of the function and the parameters, the arguments of the function, are straight out C++, right? So these two items are just generic C++ programming. The only difference is these triple chevrons. This is CUDA specific. And what this, the way that you basically call up a kernel function is just like a simple GPU, or rather a simple C++ function. You call the function and then pass the arguments within its parentheses. The way that you specify how many and in what kind of combination and architecture and coordination you want them run is through calling your CUDA kernel CUDA function on GPU with the number of blocks and then number of threads within each block that you want run. So remember, the process that I used so far is I called my CUDA kernel basically with triple chevrons 1, 1, or triple chevrons like 5000, 1, or triple chevrons size, 1. This is how I've called my kernel so far. Basically, I ran a bunch of blocks. Remember, I created a bunch of cores of my CPU, basically, kind of like, equivalent of my cores, and they would be my blocks of code, and then I had them each run one thread. The reason that I actually used a lot of blocks as opposed to using one block with a lot of threads is that I just wanted to demonstrate something really quickly to you, and that is that with using a lot of blocks, one thread each, I'm basically creating a serialized process within each block because there's not much sharing of data going on between my threads. So I didn't need to actually have any kind of local or shared data here. But we'll talk about the combinations of blocks and number of blocks and number of threads in a little bit. So let's go back to our code just for taking a quick look at how it looks like in code. And so the way that my code looks like when I called my kernel, essentially here is the piece of code that calls my CalcCubes kernel, and on many blocks, each block having one thread, basically just the equivalent of having like many cores of CPU, right? But still there's one thread within those blocks, although these will run in parallel. So essentially this is what I'm indicating. The other thing that I used a number of blocks, specified number of blocks here as opposed to one block with the number of threads, is that there's a larger limit on the number of blocks that you can run than the number of threads. Generally speaking, with the latest CUDA processes, each block can have a maximum of 1024 or 2048 threads, but there's a larger number like 65,000 or something like that on the number of threads, on the number of blocks that your GPU can run. So again, if you look at the anatomy of my kernel, I've got my basic kernel name. I've got my parameters that I'm passing to my kernel, and then the number of blocks that I want this kernel to run, and how many threads in each block I want to run. So as I said, since I wanted to show you a massive number at first to process, you have a larger limit on the number of blocks at a time that your GPU can handle. But each block can only have up to 512 on older GPUs, or all the way to 2048. Sorry, this is a typo. So all the way to 2048 threads in more recent GPUs that you can have per block. As you see here, this number of threads per block is kind of limiting, right? But it has to do with the shared memory and how much memory you can handle, as well as the number of warps in thread blocks, and how your GPU basically handles association between warps and GPUs and so forth. But with the combination of blocks and the large number of blocks you can have, and the relatively large number of threads that each block can have, you can actually think of a massive number of parallel units that you can literally run all at the same time on a single GPU. So now let's take a look at how we would actually make this call. How would we go about and decide how many threads, how many blocks, and so forth do we need? Let's just hypothetically take a look and see what if we had a our input array size was 4096. How would we call 4096 threads in one format? Or rather, just to simplify this task, let's make it 2048. How would we call 2048 threads? One option is to basically allocate one block and have it run 2048 threads, or make two blocks and have them run 1024 threads each, or have four blocks, have them run 512 threads each, or 8 blocks, each running 256 threads, 16 blocks, each running 128 threads, 32 blocks with 64 threads each, 128 blocks with 16 threads each, 256 blocks with 8 threads each, or even go all the way up to creating 2048 blocks and have them each run one thread. Which one should we prefer, and which one actually is doable, and which one is actually not doable? Remember, I said that there's a limit usually on how many threads per block your GPU can handle, and that limit determines the maximum number of threads that you can have. So if you're working with an older graphics card, the answer to these two questions may be no, right? Because if your GPU cannot allocate more than 512 threads per block, you will not be able to create one block and have it run 2048 threads, or two blocks and have them run 1024 threads. So that's one basic factor. That's one limiting factor on how many threads you should have per block. So the problem essentially becomes that. Also, furthermore, to elaborate a little bit more on this, and we'll get to this a little bit later, basically towards the end of the semester, when we talk about optimizing of your parallel program, each the GPUs have a concept of warp, and the warp is basically 16 or 32, depending on the GPU, threads. And the way that your GPU runs or allocates threads to blocks and then blocks to your streaming multiprocessors is by utilizing the packaging of threads in units of 16 threads or units of 32 threads, and then allocating them for coalesce memory accesses and for scheduling purposes, basically. And then when one thread is run, all of the 16 threads or all of the 32 threads within its warp are going to be allocated and run. So basically your GPU runs warps as opposed to individual threads. And so for this kind of purposes, it's usually a good idea to have your threads in terms of 16 or 32 threads per block, and then associate as many blocks as you need with these many threads in each, to be able to have your entire data process. So the second factor that determines the number of threads you want to use and the number of blocks per threads you want to use is the fact that how large your data is, and also how much local sharing of memory you need between threads. And we'll get into this also, sharing of memory, a little bit later when we talk about memory patterns and communication patterns for CUDA programming, in that when you have a bunch of threads in a block, those threads will have access to a local shared memory. So if you need these threads to be able to communicate with each other, you can do that through their shared memory, which is shared between all the threads within that block. So if you needed larger local sharing of data between threads, you would have to use a larger number of threads per block, and so forth. So we'll get into these later, but basically the two items that determine the breaking down of your number of threads you have between how many blocks and then how many threads per blocks you need is the fact that there's an upper limit on the number of threads that you can run. For optimizations, there's a specific number of threads that would be a good idea to allocate per block, and then and that depends really on the problem, and then on the fact that you would need to have and how much sharing of data needs to be done between threads. So all the examples that we talked about so far, block sizes and thread sizes, are one-dimensional. So for example, for that particular example of 2048 threads, we could go about and create 4 blocks: block number 0, block number 1, block number 2, and block number 3. And notice that these block indices are going to be essentially associated to a variable called block IDX. And then within each block, we could have 512 threads. So each of these will have a thread IDX. So this is going to be thread IDX 0, and this guy is going to be thread IDX 511. And that would be the same thing for all these. So all thread index for these guys, the last guys in each block, is going to be 512, right? And then the first thread within each of these blocks will have the thread IDX of 0. Okay? Or you could basically go about and create 512 blocks and have each of them have 4 threads. So in this case, your block indexes would range from block index 0, block index 1 for this guy, block index 2 for this guy, block index 509, block index 510, and then block index 511. And then each of these will have a thread index of, or thread IDX of 0, 1, 2, and 3. And then your thread indices for each block are going to be again 0, 1, 2, and 3. Thread index 0, 1, 2, and 3, and so forth. So this is the breaking down of your memory patterns. It is absolutely dependent on the maximum number of threads that your GPU can handle per block, and how much memory sharing you need to do, aside from these two facts, and optimization purposes, of course, which is kind of a micro optimization, really, if you want to think about it. Aside from that, it's up to you on how many threads, how many blocks that you need to associate and allocate. Also, one last thing is that the size of data that you can process is going to be the size of block times the size of threads within each block. That's how many you can handle. So, coming back to our block and thread sizes, CUDA allows you to use multi-dimensional blocks and within each block to have multi-dimensional threads. And this is actually a really wonderful feature that basically help us create our thread application and the running of them and our kernel programs really map with the input data that we have. Remember that the data that we send into our program is going to be in the form of a one-dimensional array that's basically coming off of your shared or your global memory in terms of your parameters that you send to your kernel. So the input data that you're going to be working with is going to be one-dimensional here. The input and output data and so forth. But how you can lay your kernels, you can actually lay them into a grid of 1 dimension, 2 dimension, or 3 dimensions, and then have each of those blocks have either a size of 1 dimension, 2 dimension, or 3 dimensions. Let me give you a quick example. Let's say that for our example, our array is basically a one-dimensional array, right? So it's basically a one-dimensional array from 1 to 1024. And then we wanted to run this program on this one-dimensional array. So your array is going to be basically something like this. Now to map this, what we can do is that we can create a one block, right? And have it have 1024 or 1024 arrays. This way you've got like one array, one thread here, one thread for this item, one thread for this item, one thread for this item. And so basically one thread per memory unit. Now let's suppose that your structure of the input changes, and say that instead of an one-dimensional array of items, let's say that you wanted to process a two-dimensional image. Okay? So how could you go about allocating a two-dimensional image to your program? You could still use, if for example this was a I don't know, like a 100 or rather what am I going to do, like a 10 by 10 image, 10 pixel by 10 pixel image, or let's do it at like a 20 pixel by 20 pixel image, like a little bit bigger. You can still go and create a block, right, of 400 threads, and this way you'll be able to basically allocate. So each thread will basically get, so you have a one-dimensional block just like this, and this was going to have a bunch of threads in it. You could with one dimensions, you could still do this and allocate each of these items, each of these pixels to a thread. Or what you can do is you can create a two-dimensional block. So you still create a one-dimensional block, and then within this one-dimensional block you create a two-dimensional thread pattern, and we'll get into this a little bit later. And that way basically each thread in two dimensions is going to have two values, two indices, an index on the x and an index on the y, which makes your mapping a lot more easier with your image. So basically your threads would then look like something like this. Okay, so each of these threads then is going to have two values, two indices, a thread index dot x and a thread index dot y, which basically specifies its location within that two-dimensional block. So using these three-dimensional, DIM3 construct, DIM3 structure allows you to create multidimensional arrays of blocks. Within each you can create multidimensional arrays of threads that then you could utilize their x, y, and z values to map them into the input data that you are processing. Whereas if you did a one-dimensional block of threads, then each of these threads will have a thread index dot x, which would be its one dimension offset inside of the thread block. So how you can specify this is through the calling of the function, the structure, dim3, and then you can pass x, y, and z to allocate or to specify its dimensions. So if you wanted a three-dimensional value, you do a dim3 like 200 by 200 by 200 or something like that. If you wanted a one dimension, you can do a dim3 w, 1, 1, or just simply call dim3u. That would create a one-dimensional array of threads or a one-dimensional array of blocks, depending on whether you put it in the grid location for your function call or your kernel call, or your block or your thread block size dimensions. So how am I going to go and create and call a multi-dimensional kernel on a multi-dimensional grid or a multi-dimensional block? So so the way that we call is going to be still the name of the function. So this is your kernel name, then your parameters, which are going to be, if you pass stuff from the global memory, it's going to be your, or rather your global GPU memory is going to be pointers, and then the size, you specify your grid size as dim3 grid size x, y, and z, and then dim3 block size x, y, and z. So this would create for each block b sub bx times by times bz threads in each block, and it's going to be a three-dimensional block, essentially like that, right? So it's going to look like that. So this is going to be its x-axis, x dimension. This is going to be its y dimension, and this is going to be its z dimension. And so basically you can, so these are each threads within the block. So this is one block. And then you can also associate a large number of these blocks. And so if you look at those, and let's draw these in a different color actually. Let's draw these. These are my blocks now. So each block, you can create a bunch of these blocks. Okay, so each of these blocks, if you for example take a look at like this block here. So this is going to be your grid X, your grid Y, and your grid Z. And so each of these, so now this guy is going to have, it's going to have those so this guy is going to have that many threads inside of it, right? So you're going to have a bunch of threads running within a three-dimensional block of threads, and then then you can have three-dimensional structures of these blocks to be able to allocate your data. So this will give you really a huge amount of flexibility in terms of mapping your input data to your output data, or rather to your threads that are going to be processing this data. So the good news is that when you run this kernel, the CUBES kernel, for example, in this case, on a three-dimensional grid of blocks, each will have a three-dimensional structures of threads are running inside. Each thread will know these parameters about itself. It will know its thread index, and its thread index is going to be its own index within the block that it belongs to. And so in terms of a three-dimensional structure, this is going to be your thread index dot x dot y and dot z. So your thread knows its own location in its block in x, y, and z dimension. Then the thread also will know the size of its own block. So for example, if the size of your block was like 10 by 10 by 10, your thread will know that the block dimension is going to be 10 by 10 by 10, or 1000 in size. Also, the thread knows its own block index. So if I have a two-dimensional block of threads, and then that to be also two-dimensional, right? So if you look at this, my thread will know its own thread dimension. So the threads here will know their thread index, right? So the thread index dot x and y is going to be their value here. They would also know the size of the block in both x and y axis. So for example, this block will have a block index dot x and dot y, and so will this block and dot y, and so on and so forth. And then also your threads will know the grid dimension. So your threads will know that in total how many in x and y and z dimension blocks are run. And so all this information is available to your threads. So again, each thread knows its own index in terms of thread idx.x and thread idx.y if I were to use a two-dimensional index. And then they would also know their block index, block idxy and block idxx, which is going to be the location of their block in the whole blocks of or the whole grid. They'd also know that what is the size of the block, which is going to be thread index and thread in x and y and z, and the grid dimension, which is going to be number of blocks in x, number of blocks in y, and number of blocks in z that has been invoked and created. So each of these little guys are going to be one thread. So each of these will have a thread index, x and y, and basically each of these blocks then are going to be made of all those threads. And that is how your kernels are going to be invoked and placed in your GPU when you call up these functions. Now, with this, I'm going to start, or I'm going to talk about what we did so far, and then we're going to go into our program, and we're going to play with this program a little bit and manipulate it, and try to get a little bit of a experiment and practice with this cubes program, and get to know a little bit about our program before we go and start with patterns of communications between threads, the kinds of operations that we can run on CUDA and actually would be efficient and parallelized on CUDA to the best extent possible, and then we'll take it from there. So what have we done? What did we do so far? What I did so far is that I had an array, and this array contained a bunch of numbers. And what I wanted to do, what I was interested in, was the cube of this array. So what I was interested in was to know what is each element in this array, its value raised to the power 3. So essentially, I had a nice little process here that I could fully parallelize. And that was take each of these elements, raise it to the 3, and put it in the final value. And that turned out to be a very parallelizable problem for me, because all I needed to do is to create a program that raises a number to the power 3, then give it to my GPU and have it associate each program to one unit of input and one unit of output. So when I hand this problem to my GPU basically runs a bunch of these threads, each of which is going to raise a number to the power of 3, and then have each of these threads to read from one specific location and write into one specific location of my output. So basically I had a kernel, and my kernel basically takes an input, raises it to 3, and then puts it into an output. Then what I did is that I said, well, let's do this. Let's run the ith kernel on the ith element of input and have it to write in the ith element of output. And that's how I parallelized my problem. This is a very simple operation, and this operation is called a map. We want a set of items to process. We know how to process one of those items at a time. The map operation basically operates or is essentially the operation we do on each of these items. Takes one element as input, generate one output per input element, and then perform the operation on elements independently of each other. So if you think about this pattern of problems that we had so far, was I had an input array and I wanted to generate an output array. For each input unit, I had one output unit that I needed to generate. So all I need to do is to specify the functionality that performs the output for one element from the input array, and then have it run, and just a mechanism to associate that process with the number in the array, or the element location in the array. And this is called map. The neat thing about map, and if you have a problem that can be expressed in the form of map, is that you're done. All you need to do is to write a serialized kernel that works on one element of data at a time, and then associate that element or that thread's index to the location of the data within the input array and the output array that you want processed. So basically, all you need to do is to create a one-dimensional block of arrays within each block to have a one-dimensional index for threads, and then just associate them. If you had a two-dimensional data pattern that you wanted to run, you could create an array blocks and block threads of or block grids, and then thread blocks of 2 dimensions. If you had 3-dimensional data, you can create 3-dimensional grids and blocks and just have them just associate one to one. So this is essentially a very simple operation, a very simple process. Again, it's called map operation. It's a one-to-one process, and of course it's map essentially because of that purpose. A map operation is essentially a one-to-one operation. Takes one unit of data, create one unit of output per unit of data, and then it can be done independently. So each unit calculation is going to be independent of other units calculation. This is the simplest operation that can be easily parallelized over in your GPU and with CUDA programming, and it's relatively easy to perform. So to finish this process and our first programming lab in CUDA, what I'm going to do is that we're going to go to our program, and then we're going to experiment a little bit with number of threads and number of blocks, and very straightforward. I'm not going to do any benchmarking here. I'm just going to show you how you can actually run these threads, and then I will show you the first project, which is going to be a real application of map on color images. So notice here what I had is I had the size, which was the size of my input, and I essentially made that the number of blocks that I ran to calculate the cubes of my data. What if I wanted to use n threads per block? And this is usually how we perform our operations. I'm going to create a constant integer, and I call it n, and let's make this n equal 16. 16 will be the size of my block. I want to run a one-dimensional block of data with threads, and each of those one-dimensional blocks, I want them to have 16 threads inside. So if I have size, which is the number of data elements that I have, basically what I'm going to do is I'm going to call my kernels with n units, And then what I'm going to do is that I'm going to divide my kernel by the size by n. One of the things that I want to be a little bit careful about when you perform things like this is you need to be a little bit careful in that the number of threads and number of blocks, basically your threads, your block size and your grid size must be whole numbers. They need to be integer numbers. And size may not be actually a power of 2, which is 16, which is the number that I have. So for that purpose, I'm going to make sure that the size that I'm using here, I'm going to avoid using things like 5,000. So for this, I'm going to use things like 4096, which is 4 times a number that is a multiple of 16. So I won't get into fractional numbers and stuff like that. Another alternative is essentially to create whole blocks and threads, and we'll get into this a little bit later, especially with your image processing project. You need to specify the number of blocks and the number of threads, and then that is larger than the input data, and then within your kernel, you're going to basically take care of if the number of thread index and block index is outside of the bound of your data. You just don't process that thread. Basically, that's just you just put an if statement and just jump over that thread if it's outside of bounds. So for this purpose, I'm going to use an array size of 496, and then I'm going to split that array size into a 496 divided by 16, which is going to be 256 blocks, and each block to have the thread size of 16. So basically 16 threads in each block. Then what I'm going to do is I'm going to go to my kernel, and then in the kernel calculation, I'm not going to use the index as just a block index, because the block index is going to go from 0 to 255 because I split the size. Now I need to use this and then associate with it the thread index. So this is going to be thread index dot x plus block index dot x times block dimension dot x. So I'm going to multiply the block dimension by the block size and add that to the thread index. So my thread index dot x 0, actually thread index dot x. So my thread index dot x 0, so the thread 0 of block 0 is going to be index 0. Thread 1 of block 0 is going to be 1. Thread 2 of block 0 is going to be 2, all the way to thread 15. Then thread 0 of block 1 is going to be number 16, and so forth. So this is basically my one-dimensional threads with 16 threads. And then I'm going to calculate the index in that way. So let's run this program. And the program works just as we expected it. It calculates the values. To make this a little bit more visual, I'm going to make my output, actually, I'm going to create a function that shows the output calculation of my cube array. And I'm going to call this function show results. And then I'm going to pass to it C. And then let's write the prototype of this function. Void show results int pointer C and unsigned int size. So let's for showing the results, I'm going to pass C and array size to it. let's go write this function then. So my function that shows the result void show results int pointer res unsigned int size. Then what I'm going to do is I'm going to show this because I have now 4096 elements. I want to split it into a bunch of rows, so I'm going to create int um, row size equals 10, and then I'm going to go for int I equals 0, I less than size I plus plus. Actually, let's do this. And then here I'm going to run for so we'll do printf %d and a space, and then c or rather result I. Okay, so this will print my result. Then if I % row size, so if I'm at the 10th element, then I'm going to printf a \n. So for the 0th element, I'm going to actually, let's first print \element there, and then so for the 0th element I create a new line, and then I write all these numbers. Oh, my mistake was this. If it's not the 10th element, now this is more like it. Okay, so as you see, I have 4,000 elements, and the first element raised to the cube of 0 is 0, the cube of 1 is 1, the cube of 2, 3, 4, 5, and the cube of 9 is 729. And it's going to basically show all those numbers, and 4,096 elements that it calculates the cube of. It could be we could have our array size to be I don't know, like 32, and this would run 32 elements, as you see here, and calculates the cube. So basically, with 32 elements, you're going to basically run 2 blocks of 16 threads each. Let's go and put another printf at the end here. Okay, so we've got 32 elements that shows basically the output. Just make it a little bit more fancy, so I'm going to go C of %d equals %d, and it's going to be I comma so this is going to show you C sub 0 is 0, C sub 1 is 1, C sub 2, and so forth. Make this then a little bit neater. Okay, that's better. C sub 0, C sub 1, So let's make this, instead of 10 units, 10 elements on one row, let's make them like, I don't know, like 7 elements on one row, which is going to be more pleasant to see. Okay, so C sub 0 is 0, C sub 1, C sub 2, and so forth. I'm just making my output a little bit more organized, and I think this is as good as I could get it to show. So C sub 0, 0, and kind of format the output to look a little bit more organized. So I had 5 elements on a row, and I formatted my output. So this is the final print out of my output. My input element was a 32 element here, just for you to see it, so it looks a little bit more organized. I made 32 elements. I have 2 blocks of 16 threads each, and then each input element ranges from 0 to 9, and then goes back from 0 to 9, 0 to 9, 0 to 9, and then I calculate my output with my CUDA program. And this is the very basic version of writing a map operation in CUDA in 1 dimension. So this is our first programming lab, and I hope that you enjoyed this program and that you learned a little bit, and I hope that you will start working on your project 1, which is going to be getting an input image in color and making it grayscale. Have fun.